Hello. Okay, so today we are starting our day with learning some um one of the important topics in AI, that is the transformer. So if we go in for any interview or if we want to start with basic, transformer is the one that people generally look for. So I'll be covering Transformer first, and then as we go, we will be covering other topics and in details. Okay, so let me just get my tablet running so that we can continue here. It might take some time. So this should do just fine. Let's see. Time. New. Right. Move this here. Yeah, that should do. Okay, so basically, I just want to take some notes um, as I'm going through these topics, but it's not really necessary there. Let me just refresh it so that it could fit in a page. Right. Yeah, for learning Transformer, I'll be just going through this website, and that is something like I just found on the net what makes the best for explanation and for understanding purposes. What's the best website for it? So yeah, so they already have given an example and how it is being processed here. Instead of that, I'll just first read through it and then we can see the explanation. Okay. So we have all heard what the transformer has as like a buzzword. So what is a transformer? So transformer is a neural network architecture that has fundamentally changed the approach to artificial intelligence. Transformer was first introduced in the seminal paper Attention is All You Need. So if you have gone through any of the AI videos or anything, so they do mention this paper. This was the paper that kind of changed the history. So it was published in 2017 or 2017, and has since become the go-to architecture for deep learning models. So all of the powering text generation model like OpenAI, GPT, Meta's Llama, and Google's Gemini. Beyond text, Transformer is also applied to audio generation, image recognition, protein structure prediction, and even game playing, demonstrating its versatile across numerous domain versatility. Okay, so yeah, basically attention is all you need is the paper that was published in 2017 and is actually the foundation for all of the models that we see like GPT, Llama, and Gemini. It works for text, image, speech, and other things like protein and okay. So fundamentally, text generative transformer model operate on a principle of next token prediction. Given a text prompt from a user, what is the most probable next token, a word or a part of word that will follow this input? So it is based on next token prediction. The core innovation and the power of Transformer lies in their use of self-attention mechanism, which allows them to process entire sequence and capture long-range dependencies more efficiently than previous architectures. Okay, so what it introduced was self-attention. Okay, so GPT-2 family of models are prominent example of text generative transformers. Explainers is powered by the GPT-2 small model, which is 124 million parameters. While it is not the latest or the most powerful transformer, it shares many of the same architectural components and principles found in the current state of the art models, making it ideal starting point for understanding this. So the explainer that we see here is actually the GPT-2 model that has been put. It comprises of 124 million parameters. Okay, so let's come down to transformer architecture. Every text generative transformer consists of three key components: embedding, transformer block, and output probability. Okay, so let's go to the architecture. So first is embedding. So text input is divided into smaller units called token, which can be a word or subwords. These tokens are converted into numerical vectors called embeddings, which capture the semantic meaning of the word. Okay, so what happens is it comprises of word, let's say hat, bat. So these words are converted into a vector, 1.0.35 and 0.7 or something. So that vector size depends on um, how we are doing the embedding. So yeah, so something like this and zero point 0.8. Okay, so basically this represents a vector in space. So this would be hat, this would be bat. So this actually also means it carries the semantic meaning. So let's say we have a boy, then it would be coming somewhere here, which can wear hat as well as use bat, or we could be moving it here, where like the boy would be the human, and these are the objects. So yeah, that is how embeddings are done. So what it actually means is we are just taking um, text input and we convert um, smaller units into tokens. So that could be word or subwords. So we are not specific to, like, let's say hat. It could be more than that or less than that. And these tokens are converted into numerical vectors. And this is, or this process is called embedding. which captures the semantic meaning of the word. Okay, so that does that. Second is the transform block itself. So like we have like input processing and output. So in the processing piece we have the transformer block. So in the fundamental building block of the model that process and the transforms the input data, each block includes attention mechanism and MLP layer, so multi-layer perceptron. So attention mechanism is the core component of the transformer block. It allows token to communicate with the other tokens, capturing contextual information and relationship between the words. Okay, so this is actually just captures contextual information and relationship between words. Basically, it helps in the probability of finding what's the next word. Then the MLP or multi-layer perceptron layer. Okay. Feed-forward network that operates on each token independently, while the goal of the attention layer is to route information between the tokens. The goal of MLP is to refine each token's representation. Hmm. Now this is something that I didn't get. So we'll just ask Gemini for it. Does it? Okay. Pro model. Okay. No issues. That is fine. Um, we can move to the third one. I'll just get back to on the multi-layer perceptron layer. So the output probability. So the final linear and softmax layer for the transformer that transforms the process embedding into the probability, enabling the model to make the prediction about the next token in the sequence. Okay, that's just a linear and soft max layer. And the transform the process embedding into probability. Okay, huh. The foundational architecture class feed-forward network, multi-layer neuron connected in directed graph. When the developer MLP MLP layer, they are almost always referring to dense or fully connected layers. And every, okay, that's how it looks like. Under the hood, MLP layer performs a simple and most powerful, a fine transformation followed by a nonlinear activation for a given layer. The output vector, okay, that is fine. Weight into the input vector and plus bias or flat architecture. Okay, hidden layer output. The final layer maps the hidden transformation, um, hidden representation of the desired output. That is fine. That is uh, okay. MLP block often refers to as a feed forward. Process the data immediately after self-attention mechanism. The attention layer determines where the model should look for context across the input, while MLP layer computes what that context actually means. So, attention layer provides us the context of the inputs of individual tokens in the vector space, and MLP layer just commutes what that context actually mean. Mm, Mental model how it's best to view them through the lens of orthogonal operations, sequence mixing, and channel mixing. Okay, that's the where and the what. Okay. So attention or self-attention is especially a dynamic routing mechanism that determines how much weight each token should give to every other token in the sequence to build a contextual representation. Okay. Attention simply averages the features vector of other tokens. It gathers the context, but it relies entirely on a linear projection by itself. It lacks the non-linear capability or capacity to compute complex higher order representation of what that combination of feature actually means. MLP, the what channel mixing. Once the attention layer has pulled the relevant context from across the sequence, that new contextualized vector is passed to the MLP block. The position wise feed forward, okay, operates strictly on a per token basis. It does not look for any other token. It looks for aggregated d-dimensional vector for token I. If attention realizes the word bank is heavily associated with river and pull those features, MLP layer process that combine feature vector and output the transform vector representation of the concept geological edge of the water body rather than financial institution. Okay, so if okay, so I got it. So attention is just a single reference um, where that word or vector is situated in the space, and what it means is derived from the MLP. That's fine. Yes, that is fine. Oh, okay, got it. So I think while the goal of attention layer is to route information between tokens, the MLP goal is to refine each token's representation. Right, got it. So basically, if we see it here, so NLP, oh sorry, attention mechanism will represent it um, in the vector space with the like information between these tokens. And the goal is to, or the goal of MLP, multi-layer perceptron, is to refine each token's representation. So what it actually means with reference to the boy is what I'm thinking. We can come back to this point later. Let me just highlight it in red. Got it. Okay. Um, but basically here it's a feed forward network, and it has the goal of attention layer is to route information between tokens. This would be between tokens information, and this will be refining each token's representation. Okay. Yeah, and output is just a linear softmax layer which transforms the process embedding into the predictions for the next token sequence. Okay, so here embedding, let's say you want to generate text using transformer model. You add the prompt like data visualization impulse uses to. This input needs to be converted into a format that the model can understand and process. This is where the embedding comes in. It transforms the text into numerical representation that the model can work with. To convert the prompt into embedding, we need to first tokenize the input, obtain token embedding, add positional information, finally add up token and position encoding onto the final embedding. Let's see how it's done. First, this is our prompt. So data visualization empower users to, and the next word or token, what that would be. So what it does, let's cover from here, embedding. So first it takes token, and then it what it does is token embedding, and then positional embedding, and that is equals to our actual embedding. So let's understand what this positional encoding, oh sorry, encoding here, embedding encoding. Right. So um, tokenization. Tokenization is the process of breaking down input text into smaller, more manageable pieces called tokens. These tokens can be a word or a subword. The word data visualization corresponds to unique token, while the word empower is split into two tokens. The full vocabulary of tokens is decided before training the model. GPT-2 vocabulary has 50,257 unique tokens. Now that we can split our input text into tokens with a distinct ID, we can obtain their vector representation from embedding. So that is tokenization. um, word to token, which is already set in GPT-2 or before training and before training the model. Okay. And in GPT-2 we had around 52,000. Oh, sorry, 50,257 tokens. Okay. Now the token embedding. So GPT-2 is a small GPT-2 small represents each token in the vocabulary of 768 dimensional vector. That's what I was saying. Here the dimension size depends on what model that is or how we are doing that. So token embedding. So GPT-2 has 768 dimension vector. Okay. Um, the dimension of the vector depends on the model. These embedding vectors are stored in the matrix of shape this because that is like sorry, that's because it's 50,257 embeddings and 768. So whichever word um, so representing word, we would need to convert it into tokens, and we have the list of tokens. From there, we can just represent zeros and ones for that. Containing approx 39 million parameters. These embeddings are stored in a matrix shape this, containing approximately 39 million parameters. Okay. This extensive matrix allows the model to assign semantic meaning to each token, in the sense that token with similar usage or meaning in language are placed close together in a high dimensional space, while dissimilar tokens are far apart. Okay. Semantic meaning close. Okay, that's done. So coming to step three, which is positional encoding. The embedding layer also encodes information about each token's position in the input format, or input prompt, sorry. Different model use various methods for positional encoding. GPT-2 trains its own positional encoding matrix from scratch, integrating it directly into the training process. Okay, that's fine. So basically, this is the information um, of the word or token. It's a word in the prompt. Information of position of the word. Information about position of source. That's right. Okay, so transformer block. The core um, of transformers processing lies in the transformer block, which comprises of multi-head attention, multi-head, self-attention, and multi-layer perceptron layer. Okay, most model consist of multiple such blocks that are stacked sequentially one after another. The token representation in evolves through layers from the first block in the last to the last one, allowing the model to build up an intricate understanding of each token. This layer approach leads to higher order representation of the input. GPT-2 small model we will examine consists of 12 such blocks. Okay, so 12 blocks of multi attention, oh, self attention, and multi-layer perceptron layer. Okay. Okay. So we will be going one by one with these topics. Okay. Multi-head self-attention. Oh, that's the name. I created two of them. Okay. The self-attention mechanism enables the model to capture relationships among tokens in a sequence so that each token's representation is influenced by the others. Multi-attention head allows the model to consider these relationships from different perspectives. For example, one head may capture short-range uh, syntactic links while another tracks broader semantic context. The following section, we will walk through how multi-head self-attention is computed step by step. Okay, step one, query, key, and value metrics. Okay, query, key, and value matrices. Okay, each token embedding a vector is transformed into three vectors: query, key, and value. These vectors are derived by multiplying the input embedding matrix with learned weight matrices for QKB. Here is a web search analogy to help us build some intuition behind the matrices. Okay, a query is the search text you type in the search engine bar. This is the token you want to find more information about. Okay. Key is the title of each web page in the search result window. Okay. It represents the possible tokens the query can attend to. Value is the actual content of the web page shown of web pages shown. Once we match the appropriate search term query with relevant values of relevant keys, we want to get the content value of the most relevant pages. All right. So once we do the search, we take the query, search it. It will list down all of the pages, web pages, or the keys in this case, and these keys would have values, or the content will have values. So that content is the value of each pages. Okay, by using these QKV values, the model can calculate attention score while determine how much focus each token should receive when generating predictions. Okay, query is something we need information about. Need info about key are the web pages, and value is um, details in the page or content of the page. Okay, this is analogy, not what it really means, but yeah, I think then step two. By using KQE, the model calculates attention score, which determines how much focus each token should receive when generating predictions. Okay, let's move this. Model calculates attention score. Um, and this attention score is used for determine focus each token should receive when generating prediction. Yes, for each token. Okay. Multi-head splitting. Okay. Now we have the query key and value. I think here we can see we have the embedding. We have these values of Q, K, V, and okay, those are the weights, and this is the bias. So after um, doing this embeddings into weight plus bias, we get this QKV. Okay. Yeah. So multi-head splitting. Vector are split into multiple heads in GPT-2 small case into 12 heads. Each head process a segment of embedding independently, capturing different syntactic and semantic relationship. This design facilitates parallel learning of diverse linguistic features, enhancing the model's representational power. Okay. Okay. Here, QKV vector is split into multi-heads. In GPT-2 case, it is 12 heads. Okay. Each head process a segment of the embedding independently, capturing different syntactic and semantic relationship. Okay. Step three, mask self-attention. In each head, we perform mask self-attention calculation. This mechanism allows the model to generate sequence by focusing on relevant part of the input while preventing access to future token. Okay. Hmm. Okay. Mechanism allows to generate sequence by focusing on relevant part. Parts of input while preventing access to future. I think this is okay. Those are the short notes. So we don't really need to make it. This is for my own. Let's open share information. Refines each token's detail. Okay. Uh, let's do this. Um, and yeah, so the mechanism allows the model to generate sequence by focusing on relevant parts of the input while preventing access to future tokens. So it generates the sequence and focus on relevant parts of the inputs, whatever the words are behind, and it can see what's in the future or the next word. Okay, so dot product. The dot product of query and key matrices determines the attention score, producing a square matrix that reflects the relationship between all input tokens. Okay, scaling and masking. Scaling dot mask. So dot product. The attention scores are scaled and mask is applied to the upper triangle of the attention matrix to prevent the model from accessing future tokens. Setting these values to negative infinity, the model needs to learn how to predict the next token without peeking into the future. So the next half is disabled, and we have like just here the tokens. Okay, so softmax and dropout. After masking and scaling, the attention score are converted into probabilities by the softmax operation. Okay, then optionally regularized with dropouts. Each row of the matrix sum to one and indicates the relevance of each relevance of every other tokens to the left of it. Okay, so this is the key, this is the query, and these are the values. So basically, we are doing um, the dot products between the key and the query, where we will see, let's say, this is data, this is data visualization, and we have like all other values with the dot products for each of the word combinations. Now, what we do is we just remove the top right part of this matrix in the scaling and masking, and that creates um, data, data visualization, uh, uh, sorry, yeah, data visualization or visualization data and all of that. So this is the matrix, and now we need to find out what would be we find by taking masking and scaling. Sorry, after masking and scaling, the attention scores are converted into the probability by softmax operation. So we apply the softmax operation on this. So here you can see the value were between minus 25.3 to 7.4. After scaling and masking, it came to minus 3 to 3, and then we just did the softmax and dropout, and we got the value between -1 to 1. Then the optional regular, so we regularized with the dropouts what the values were. So each row in the matrix sum to 1 and indicates the relevance of every other token to the left of it. So here the sum will be 1 for each of the rows. So this is 1. So you can see this 2 would add up to be 1 and all of that. So that's the softmax robot. Okay. Um, Here step 3, right? So first we do is key dot query. This is dot product. Then we do the scaling and masking. Masking where we hide this um, top right or the right side of the matrix. And then we do a softmax and regularization के लिए हम लोग drop out करते हैं, which is optional but we do. Okay. So this every row will result in a value of 1. So we can get the probability here. Okay. Now the step 4, output and concatenation. The models used the masked self-attention score and multiply them with the value matrix to get the final output. Okay. Here, right. Now this into the value will result in output. Okay. Um. Yeah. So step 4 we do this, but it's already there. So output and concatenation. So the model used the mask self-attention score and multiply them with the value methods to get the final output of the self-attention mechanism. GPT-2 has 12 self-attention heads, each capturing different relationship between the tokens. The output of these heads are concatenated and passed through a linear projection. Okay, output is actually step 3 में जो भी किया into value, and then this like it will have like this is the final output of the self-attention mechanism. Self-attention mechanism का ये output है. But we have like 12 of these, 12 heads are there. So what we do is um, each capturing different relationship between the tokens. That is true. The output of these heads are concatenated and passed through a linear projection. So like into 2 12 10. So this is here concatenated and passed through a linear projection. Okay. Then comes the MLP. So after the multi-head of the self-attention is captured, the diverse relationship between the input tokens, the concatenated output, are passed through a MLP layer to enhance the model's representational capacity. The MLP block consists of two linear transformations with GLE, GELU activation functions in between. Okay, Gaussian error linear unit. Okay. So this is done. MLP, right? Layer. Okay. So MLP enhances models representational capability. The MLP block consists of two linear transformations with a GELU activation function routine. Okay. Two linear transformation with GELU activation function. Well, I know ReLU and other things, but it is GELU. Gaussian error linear unit. Error linear unit. And it is represented with the Gaussian function. Okay. Mm, X is equals to by 2 1 plus mm, that is what is that? Cumulative distribution, normal distribution, and this is the error function. Okay, error function of x by root 2. Nothing knows Russian function formula. Mm, well, not this one. Well, we can go through that later. This activation is illustrated in the figure at the start of the article. It has a bump of negative derivation to the left of x is 0. It serves as a default activation for many transformer models such as BORT. Okay. The start it says right. Okay, this is the one. Okay, got it. It looks like that. Something on the lines of real, but somewhat different. Right. I mean, this is good, but I don't think anyone is going to ask that. Neither could I explain it. So, um, ReLU is pretty simple. Tell 0 at 0, and then from it's linear. Then this is ReLU, and this is GLU. Uh, doesn't touch 0. Bumped, and then it goes here. Okay. Okay. Anyways, we can move this and this. Yeah. So MLP block consists of two linear transformation with GLU activation functions in between. Okay. The first linear transformation expands the dimension of the input fourfolds from 768 to 3072. This expansion step allows the model to project the token representation into a higher dimensional space where it can capture richer and more complex pattern that may not be visible in the original dimension. Okay. The second linear transformation then reduces this dimensionality back to the original size of 768. This compression step brings the representations back to a manageable size while retaining the useful nonlinear transformation introduced in the expansion. Unlike the self-attention mechanism, which integrates information across tokens, the MLP process tokens independently and simply maps each token's representation from one space to another, enriching the overall model capability. So basically, it takes um, 768 dimensionality linear vector, transforms it to a 3072, and then it brings back uh, to the 768. And we do apply um, GLU activation function in between. Okay, cool. So let's take this. So we take 768, converts to 3072. We have GLU, and then we bring it down to 768. Cool. So output probability. After the input has been processed through all the transformer block, the output is passed through the final linear layer to prepare it for token prediction. This layer projects the final representation into a 50,257 dimensional space, which was the original tokenization. Sorry, yeah, embedding space, where every token in the vocabulary has a corresponding value called logit. Any token can be the next word. So the process allows us to simply rank these tokens by their likelihood of being that next word. When we then apply a softmax function to convert the logits into the probability distribution that sums to 1. This will allow us to sample the next token based on the likelihood. So we can see the logit was 135.91. Scaled it, take the top key, and we had done the softmax. So the final step to generate the next token by sampling from the distribution, the temperature hyperparameter plays a critical role in this process. Mathematically speaking, it is a very simple operation model. Output logics are simply divided by the temperature. Okay, temperature equals to 1, divide the logic by 1 has no effect on the soft max output. Lower temperature makes model more confident and deterministic by sharpening the probability distribution, leading to more predictable output. Greater than 1, higher temperature creates a softer probability distribution, allowing the more randomness in the generated text, what some refers to as model creativity. Okay, fine. So here we are in the output probability. So we have temperature as a hyperparameter. Let me add what it actually does, or it should be fine. No, let's add that. So we have output. It's passed through the final linear layer and prepares a token prediction. This layer projects the final representation. Okay, input layer has been processed through all transformation block. Input transformation block, and the output is passed through final linear. Output is passed through a linear layer to prepare it for token prediction. The robot token prediction. Okay. Now, this layer projects the final representation into a 50,257 embedding or dimensional space. Okay, where every token in the vocabulary is corresponding to a corresponding value called logit. So it will have logit, and any token in the next word can also be processed in a simple rank likelihood, but being the next word, we apply a softmax function. So everything will be in like sum equals to 1. Um, so the probability basically, and then we take the most likelihood. Okay, and here we have let's say temperature equals to 1. Um, to generate the next token by sampling from the distribution, the temperature hyperparameter plays a critical role in the process. Mathematically, simple operation model output logics are simply divided by temperature. So here we have temperature, and what we do is temperature, if temperature equals to 1, divide by 1, no effect, softmax. But if we set the temperature less than 1, makes model more confident. Okay, because let's say if it is okay, let's if it's 1,000, we divide it by, let's say, 0.01. So this will go up here and it will increase the value of logic. Okay. Um, So if the value is bigger, it will increase that. Okay. If we have temperature value, if we have temperature value greater than 1, then the model becomes more creative, what we say. But actually, it is just, let's say, we have 1,000, we have more than one, that's, let's say, 1.1. So basically, this will reduce this value and will give a more random answer for the next token. Okay. Additionally, the sampling process can further be refined using top K and top P parameters. Okay. Um, Top K sampling. So limits the candidate token to the top K tokens with the highest probability, filtering out less likely options. Consider the smallest set of tokens whose cumulative probability exceeds a threshold P, ensuring that only the most likely token contributes while still allowing for diversity. Okay. Consider smallest set of tokens whose cumulative probability exceeds a threshold P. Okay. So top K just takes um, top K token and it's done, like the highest probability. But top P sampling takes in cumulative relative threshold of P probability. So it is more diverse, but yet takes the highest probability elements. So by tuning temperature, you can balance between deterministic and diverse output, tailoring models' behavior to your specific needs. Okay, auxiliary architecture feature. There are several auxiliary architecture features that enhances the performance of the transformer model. While important for models' overall performance, they are not as important for understanding the core concepts of the architecture, like layer normalization, dropout, residual connection are crucial components in transformer model, particularly during the training phase. Layer normalization stabilizes the training and helps model converge faster. Dropout prevents overfitting and randomly deactivates neuron. Residual connection allows gradient to flow directly through the network and helps to prevent the vanishing gradient problem. Okay, so those are the three more parameters or the ways that are used for enhancing the performance of the transformer model. Okay, then we have the interactive features. It says, okay, let's go to the thing. Since now we know everything about how it is processed, now we can just go through the model once and see what happens. Okay, so let's say we type in what is the largest largest animal. Okay, and we click on generate. So here we did the embedding. We had like 768 vectors embedding, and we did the dropout, and then we had the layer normalization. Um, so stabilize both training interface while maintaining adjustment. That's fine. Then we get the uh, this QKV um, Wow. Okay. Yeah. So what we are doing is we are taking the embeddings, we are multiplying with the QKB weights. So this process here, we took the dot product. Uh, oh, sorry. We are just getting the value of QKB here. We are just doing this embeddings, weights plus bias. So we had the initial weights set 768 to 34, and then we had the bias value for it, and then we got the like QKB value for what is the largest animal. So we got these values. Okay, and then we have like query, key, and value. So we have like independent values for each of these. Okay, so this is head one query vector of 64, and similarly here we have the same. Now what we are doing is we are going into attention. So here we take the dot product of key and query. Then we are doing the scaling and masking where we remove the top right part of the vector matrix. Then we do the softmax. So initially the value was 3.19 after the dot product, and then we did the scaling and masking. So we got it 2.4, and then we did the softmax where each row combines value is 1. So you can see here, right? So this is done. Then we take the output and we multiply it with the value. So this is the attention what we are getting. And this is like the single head attention. We have like 12 of those. So here we have um, like 12 heads. So it is doing it 12 times, and we are just then concatenating it and concatenating the output and getting the linear projection out of it. So this is like the 768 vector space for each of this, and we did the dropout, and here we enters the MLP part. So what is happening here? So we are um, taking the 768 um, um, 768 layer and we are doing like layer normalization, let's say. Yeah, so vector space of 3072, and then we are just applying um, GLU and then taking it back to the 768 compressed bias. So this is the expanded embedding. So it's showing how we are taking what and then the compressed weights are then expanded, and then it is again compressed it back after applying the softmax function. Oh, softmax is applied here, sorry. Yeah. So the residual basically we get is a 768 vector, and now um, we have the transformer block ends here, and we get the embeddings, and then here we are doing the calculation for the logits to so output embedding whatever we got, output projection weights, transforms the final embedding into the vocabulary distribution parameters. So we had this number of embeddings and how we are mapping it. So basically converting it back to logits value, and then we have um, uh, the calculations done. Here you can see we scaled the logits. So the temperature value was zero point 0.8. So we are kind of taking um, here, yeah. So model becomes more confident. If it's more than one, model is more creative. Then we are doing the top K filtering. We will take, let's say, top five because K value is five. So it uh, takes in the top five ones and the values in is the next token that is being generated. Let's shift to the top P filtering. Cumulative is less than zero point 0.5. Cumulative is less than point, let's say 8. So you see, as we keep changing that value, it changes the words as well, right? Okay. Um, and let's say we increase the temperature. You see, it becomes more creative. So it outputs on. And if we increase it by 5, it adds species. So what is the largest animal species is like the temperature is 5, let's say 2 of is also there. If we reduce it, it just gives in. So we need, like, these are hyperparameters that we can use for um, getting those calculations done. Okay. Yeah, so that kind of summarizes this transformer explainer. Um, Now, like in the next one, I'll go through the next topic, but also revise this piece so that it is there. Okay, that's all for today. Thanks for watching. See you guys uh, in the next one. Bye.